Hello, everyone. My name is Joseph Alexander Brown. I'm an associate professor at Annapolis University and the head of the Artificial Intelligence and Games Development Laboratory. Today's presentation is on a family of turn-based strategy games with Moose. Our team for this work includes Dr. Daniel Ashlock from the University of Guelph, myself, Connor Greger, also from the University of Guelph in the Department of Mathematics, and Munir, who's my PhD student here at Annapolis in Russia. One thing that Russia and Canada both have in common is moose. As you can see, the moose ranges over both Kazan in Russia and over the areas of North America in Canada that the University of Guelph is. So we're kind of interested in the modeling of this creature. You may be familiar and may have seen various videos of moose during ruts. They are very aggressive and territorial animals, and they have evolutionary adaptations that allow for such fights. These are huge antlers that come in over the summer. They shed them over the winter months, so presently they'll be shedding quite soon, these antlers, but they use them over the summer seasons. Our idea with this model is also engaging students with the materials. Learning should not be just based on lectures and reading, but in my game 1, 2, 3. The idea of this model originally was to engage students with game theory, and through it, we used more of an active learning model, and there was contests that were placed upon this. The previous paper on this delves into said contests at Annapolis University. Active learning has been found to increase student engagement. For example, this is inside of my game theory class, 2 students having a Nerf gun duel in which we talk about how do duels work within game theory. In order to examine this behavior, we take a look at a game theoretic model. We count that there's a number of fields that can grow via a sigmoid function to produce resources that the moose like to eat. We'll examine this factor later in the study. The moose may select a field in which it wishes to move during a turn. If there's another moose there, then they aggressively fight with each other, they get no food, and the field is damaged. If they're alone, however, they will eat and the field is reduced. The winner is the moose who eats the most over the rounds within the game, in our case, 100. We can see that this is very close to the ideas inside of other game theoretic models, such as the prisoner's dilemma. However, the behaviors of this model and the prisoner's dilemma are quite different. If moose select the same field, then they fight. They end up with nothing. So this is where we kind of differ from the idea of the prisoner's dilemma, in which sometimes if you work together and go to the same location, you'll be rewarded. However, in this case, it's a discoordination problem. Moose win when they do not go to the same field and are allowed to eat. When moose select different fields, they make some amount of gains based upon what the value of the field is. We use an evolutionary algorithm in order to fight these moose models against one another. Our representation is a finite state machine that has evolved. This, for example, is an evolved 4-state machine. The initial action appears on the arrow coming in from no source, and the subsequent actions are generated by the traditions in the form of the first value is what the opponent's most recent action is and what your response is. So in this case, if I was in state A and my opponent went to move to field 1 in the last action, then I should move to field 2 in the next action and change my state over into B. This assumes that I have perfect and universal knowledge of the situation, which is perhaps not very realistic to the ecological model, however, is pretty much what is allowed inside of iterated prisoner's dilemma tournaments, in that you know what your previous actions of your opponent were. So via this, we are basically assuming for the moment that this is a perfect universal knowledge system. Over time, our moose actually begin to kind of learn what is happening through this. So in time step 5, we see that they've both arrived on field 1 and received nothing. They take a look at what fields are out there and notice that field 4 has a great deal of resources, and they both move there. We're still having some issues. However, if they split apart and break into field 1 and field 2, then they're both able to succeed and forage. As I mentioned before, the idea is we are going to be controlling the amount of growth rate within the field, as well as changing the field capacity over this sigmoidal function. There's two values inside of this. The first is how much does the field grow over a time step? How much does the amount increase? And secondly is the total carrying capacity of the field. This is very close to a number of biological models which look at these problems. In our experiments, we are constantly increasing, in the first case, the growth rate and keeping the field capacity stable. In experiments 4 through 7, we look at slowly increasing the field capacities while holding the growth rate relatively stable. In experiment 7, we increase both the growth rate as well as the field capacities. So we can see this as being a parameter search. The results, we can see that a high capacity and growth rate leads to more total achievable fitness. So there is more resources on the fields in order to be exploited. However, we can see that there's a great increase in experiment 7 that's not really accounted by just one factor alone, as you can see through experiments 1 through 3 and 4 through 6. The fraction of confrontations also goes down during this type of play, as both moose are able to move towards an empty field that still has an achievable large amount of resources that makes it worthwhile going to and eating the area there. We can see that the nominal rate on this, the most likely, is about 1/3. So moose have managed to avoid each other when the resources grow higher. When the resources are scarce, however, they are more likely to fight with one another. This definitely means less movement in the moose. And in this case, what we looked is the field distribution, the fraction of plays that are happening of each type. So we can see that as those experiments move forward, less movement happens, as moose are much more happy going to the same field again and again. The moose problem is really a family of problems. There are many different factors that we can modify within the game in order to change the behavior within the agents. But in this case, we only looked at different growth rates and biomes, the extension from the original publication. But what about the number of moose or fields that are there? Or the level of knowledge? As I mentioned earlier, we use perfect knowledge of the whole system. Yet this is maybe not too realistic. And if we're trying to put this into also a fun game that can be played and checking the balance of said game, then we would have to take into account the relative lack of knowledge of certain players. What about the movement cost between fields? In this case, it's free for a moose to move, but there might be some sort of travel cost involved. How about the health of the moose depending upon past success? Moose in the wild, if fighting with one another, usually will do damage even to a moderate amount that will cost them in terms of their abilities. Now, moose for this is interesting for the fact of we're trying to show this to a bunch of Canadian and Russian students, and the moose is an animal that both of us share and understand, but we can have other themes than a moose. Many historical options exist in which you have little city-states fighting over resources inside of it. And we delve into this a little bit deeper in the paper, but we have this idea of an empire skin in which we can change this into a more fully featured game that explores the idea of two empires fighting on the borders with various farms that they are pillaging and striking against each other. Thank you very much for your attention. Again, my name is Joseph Alexander Brown, and I'm the head of artificial intelligence in the Games Design Lab at Annapolis University. You can contact me at j.brown@annapolis.u or on Twitter at JB3HF. And I hope that you will give this a try when we finally have a contest coming out in the new year.